So welcome, thanks for joining us. Today we're going to talk about the strange magical world of Wi-Fi. Something we all rely on, but something that interacts with physical objects, but something we can't see, and it's a pain in the butt to try to figure it out, troubleshoot it, see what's actually going on out there. Even with all the tools, you spend the money, buy some expensive spectrum analyzers, it's still a bit of a pain to try to figure things out. So today we're going to go through, talk a little bit about Wi-Fi, talk about some best practices, talk a little bit about Wi-Fi 6. There we go. Now I'm starting to move through. So just in case those of you joining us here are new to Zyxel, just one single slide here to go over our background. If it works. I don't know what's going on here with my computer. There we go. So we've been doing this for 30 years. We've been making networking equipment back since 1989 here in the United States. We currently serve 150 different global markets. We have over 100 million devices deployed out there in the field. And that number hasn't been updated in a while, so it's probably a lot higher than that actually now. So there we go. Also, as we go through today, if you have questions, send them in using the Q&A box. So we'll start off with some of the basics here when it comes to Wi-Fi. IEEE is the creators of the standard. So it's an engineering group. They put just about together every standard that's out there for different forms of networking, as well as a bunch of other stuff that's out there. So they're the guys who create the standard. That's where we get, 802.11, A, B, C, AX, etc. There's the Wi-Fi Alliance, which is a group of manufacturers and the like. They get together and try to ensure compatibility between the different products. So even though they might be using the same IEEE spec, there's still some room there for interpretation. So the Wi-Fi Alliance puts together tests that everyone needs to comply to in order to be able to be certified with Wi-Fi. Generally, though, you only see Wi-Fi certification on consumer-type products. You don't generally see it that often on business-class products, although we're all still following the same basic set of rules. And then here in the United States, the FCC. They're the ones that decide which channels you can use, decide how much power you can use on those channels, and other behaviors that have to be followed by the devices themselves. So Wi-Fi works using radio waves. So the same thing you use in a walkie-talkie or the radio in your car. So we're using the different parts of the spectrum there. We have the 900 megahertz spectrum, the 2.4 gigahertz spectrum, and the 5 gigahertz spectrum. Those are the radio frequencies that we can use without needing a license to be able to deploy a wireless device. Everything else requires that. Hold on, give me just a second here. There we go. Basically, as frequency goes up, it's easier to cram more data onto that. But as frequency goes up, the harder it is for that signal to go a long distance. So if you go back to the cordless phone analogy, in the early days of cordless phones, they were 900 megahertz. You could walk a really far distance with that cordless phone and use it. I know when I was a kid, we could go outside, go down to the street, walk over to the neighbor's house, and we'd still be able to maintain a phone call. In the early 90s, 2.4 cordless phones started coming out. The big pitch for those was better sound quality. Why? Because the frequency has gone up. They can put more data or more fidelity into the sound that's going over those radio waves. But you found that you couldn't do that anymore. If you were lucky, you could go outside and maybe maintain a conversation on the yard in front of your house, but you weren't able to walk over to your neighbor's house anymore and still maintain a conversation. And then towards the mid-90s, we started seeing 5 gigahertz cordless phones. Again, improvement in the sound quality, but range was even less. Now maybe they don't work outside at all. Maybe even if you have a larger home, some corners of your house you can't really maintain a steady connection. So that all has to do with the frequency and the frequency going up. So generally when you're looking at data sheets, when you're looking at consumer products, you'll normally see milliwatts counted. They'll advertise 200 milliwatts, 500 milliwatts. When you look at data sheets for business class products, instead you will see dBi or dBm being advertised, which has to do with a different way of notating the power output. Generally, part of the reasons we like to use DBM or DBI is you can take the DBM from the chipset, the power that the chip is putting out, and you can easily add in antenna gain or subtract losses all rated in DBI losses as far as your cabling goes, your connectors goes. So it makes it really convenient and easy for you to quickly and simply add DBMs together. One of the things when it comes to DBM is every 3 DBM you add doubles the milliwatt output power. So 20 DBM gets you 100 milliwatts, 23 DBM gets you 200 milliwatts. So a lot of people go, well, if I'm going up in milliwatts, I've doubled my power, am I doubling my range? And the answer is no. We'll get to it on another slide coming up here, but the formula for calculating how far the signal goes is really complex, but it's actually much closer probably to the increase you see as a percentage of DBM than it is as you see as an increase to milliwatts. So instead of, going from 20 to 23, that doesn't double your range. It gets you a small increase in your range generally. Okay, some other stuff here. Signal to noise ratio. This is probably the most overlooked aspect when it comes to Wi-Fi when it determines your range and your speeds. So signal to noise ratio is the strength of the signal you want to listen to versus the level of other signals operating in that same frequency that you don't want to listen to. So that could be noise from other access points operating on the same channels, other wireless devices, can be RF interference put out by power supplies, air conditioners, industrial equipment, things like that. So the better your signal to noise ratio, the better your throughput is going to be. We often run into situations where people go, hey, I've got a really strong signal from my AAP, why is my performance so bad? And oftentimes the answer is because there's something else also using that same channel, causing co-channel interference to raise the noise level up so high that even though the signal coming from your AAP is strong, your device is having a hard time being able to differentiate that signal from the rest of the noise or interference that's going on in that channel. Another term here for us is attenuation. So that's just basically how much the signal degrades. So it can be over distance, it can be degradation as it passes through people or obstructions, walls, things like that. So you can see there the formula up at the top of the screen. That is how you calculate how far your signal is going to go. So you can see it's logarithmic, having to do with distance versus the frequency. So it's kind of a pain to try to figure out. If you go online, there are a number of calculators or web pages that have calculators built in where you can plug in your things and it'll tell you how far the signal can go. But again, that's also ignoring the signal to noise ratio. So again, you need to know that as well. And then just showing you some common items here. A window is going to give you a 3 dB loss of your signal strength. A tinted window, something that's got one of those metallic coatings that keeps out infrared or keeps out UV, that'll give you up to an 8 dB loss. Walls going up from there depending on what they're based out of. So just so you can see, that's how things will affect the attenuation of the signal. So another thing here to keep in mind when we're talking about Wi-Fi range, it's a combination of signal strength, the signal to noise ratio, things like that. But we also have to keep in mind that it's a two-way communication. It is a conversation. So it's not just about how powerful your access point is and how far it can send the signal. It has to do with your client device and whether it can send the signal and get it back to where the access point is. So it's similar to a conversation with people, right? So if you're in a situation where, you're both sitting across the table from each other and talking in a normal voice, you're both going to be able to have a conversation quite well. If you move one of the parties and move them to the other side of the room, and that person can shout, but the other person for some reason cannot shout back, then you're not going to be able to maintain a conversation because both parties need to be able to both send information to each other and hear the information coming back. Similar thing when it comes to signal to noise ratio. If you're talking to somebody at a table in an empty conference room, you don't have to talk that loudly for them to hear you. Go to a bar where there's a lot of background noise, in this case we would consider that noise or co-channel interference, then you're going to have to shout to be able to hear each other. In some cases, shouting isn't enough, right? You've got to shout while keeping your mouth just a few inches from the other person's ear to be able to hold any sort of conversation. So it's the same sort of thing here with Wi-Fi. Continuing on here, RF behavior. So Wi-Fi is a wave, right? We called it radio waves, and it behaves very similar to like ripples or waves in a pond. So if you drop a rock in a pond, right, you get ripples that ripple out from the center of where that is. So consider where the rock hits the water to be, say, where your access point is. And then as those ripples radiate out, they get attenuated, they become, less large. But as they hit objects, what happens? If they hit something like a wall or some legs of a dock, they may be able to wrap around that dock. They may hit the wall and bounce off of that wall, so you get reflections. You may hit something and it scatters off ripples in different directions simultaneously. That's scattering. You get something like multipath, where you can have the same wave, bouncing off and coming in and hitting another object at different times. So that's the exact same stuff that happens when it comes to RF radio waves. And my computer's freezing up. There we go. Okay. So I want to show you this here. This is, up until 802.11ax, this is how Wi-Fi devices determine whether or not they can send data. So for the Wi-Fi, only one device on that channel can transmit data at a time. So everybody takes turns. Access point sends some data, Bob's laptop sends some data, your iPhone sends some data. So they all take turns. But there is no coordination of this. So what happens is your Wi-Fi device basically says, hey, I need to send some data. It checks, is anybody else sending data? If somebody else is sending data, what happens is then your Wi-Fi device then uses a random number generator to determine how much time to wait before checking again. So it'll wait a random amount of time, check again. Is anybody else sending anything? If they are, again, another random number gets generated. It waits that amount of time and continues to do that until such time that it detects no one else is transmitting. Then it decides to go ahead and send its data. So part of the problem that you run into with this is you run into a situation where when you've got a lot of different wireless devices all using the same frequency, is you run into a situation where two devices need to send data. They both detect the same pause in data and say, hey, it's open, and then they both decide to transmit at the same time. And you end up losing your data and it gets garbled and it has to be retransmitted again later. The other problem you run into is a situation like we've got on the PowerPoint slide right there right now, which is that you've got your access point up in the middle of the room. You may have client devices on one side of the room and client devices on the other side of the room. They're both within range of that access point, but they are not within range of each other. So what happens is those devices will not know that the device on the other side of the room is transmitting. They'll think they're free to go. So you end up with devices transmitting at the same time. The AP can hear both of those devices, so those signals overlap and it can't make out what either one is trying to send. So you end up getting drop packets. This is what we call a hidden node problem. So this is another thing that sort of runs into the fact because Wi-Fi, at least prior to 802.11ax or Wi-Fi 6, didn't have any way of organizing whose turn it is to transmit or designate time periods. Instead, it was just based on random number generator and checking to see if you could hear anybody else or not. So another thing that we run into a lot with people, especially end users, is confusion about data rate versus throughput. I'm using these terms. These terms can be used many different ways, and you may see people using them differently than I am here. This seems to be, though, largely the best way to explain this and the cause of most confusion when dealing particularly with consumers. So when Wi-Fi products are advertised, right, they're advertised as certain speeds. It's an N300. It's AC2600. So those are based on the data rate. It's the industry standard. It's the way that networking equipment has sort of defined their speeds, for the last 30 or 40 years. So it's been around a long time. So the data rate, which is what the speed is that we're advertising, is also often sometimes referred to as the physical rate or the link rate. So this includes all the protocol that goes into making Wi-Fi work. So Wi-Fi is working on these 2.4 or 5 gigahertz channels that are open for anybody to use, anybody to broadcast on, with some very just basic rules. So there's a lot of interference, there's a lot of other stuff going on, so there's a lot of error checking and protocol work that goes in to make the Wi-Fi connection reliable and allow it to function in this noisy environment. So just to give you an idea here, Ethernet cables, which is where, this standard sort of came from, where you refer to the physical rate or the link rate or the data rate, has very little protocol overhead. So the difference between a 1 gig Ethernet connection and the actual maximum data you can send through it is very minimal. However, with Wi-Fi, that's not the case. With Wi-Fi, what happens is a ton of the data being transmitted is the protocol data between the client device and the access point, not the actual data you're trying to send from your application to some server on the internet or vice versa. So I tend to use the term throughput to mean the data that you personally want to send. So if you go to speedtest.net, it's measuring your throughput from your laptop over the Wi-Fi, through your router, out to the internet, to the speedtest.net servers. So that's, how much data can you send from your laptop all the way out to there. And it's only measuring that data that's coming from, the server or coming from your browser. So data rate, so that is generally going to be, because of the high overhead of the Wi-Fi protocols, is generally going to be anywhere from 50 to 60% slower than the actual amount of data that's being transmitted between devices. So that's why you'll see, if you go to Amazon and pull up the reviews, you'll see a lot of people saying, hey, it said it was a 1200 megabit product. I'm only getting 400 megabits. Well, that's in the ballpark. And that doesn't take into account signal strength issues, different, distance from the access point, RF noise, things like that. So it's very common and normal that you're going to see this huge difference between the so-called advertised speed and the throughput as measured. So we got a question. Again, if you're going to send a question, don't use chat. Please use the Q&A box, because I can't see the chat easily. But someone here, Jack, is asking, how do you test the data rate? Most Wi-Fi clients, at least in the old days, I can't remember if Windows has this now or not. I think it does. I think you can still find it in Windows 10. It might be kind of hard to find. But when you go into Wi-Fi info, it should show you what the current data rate is that it's connected at. And your client devices, if they're not sending a lot of data, will automatically go to lower data rates until you start sending a large amount of data, and then it'll take them a second or two to speed back up again. But you can find it there, and then in your interface for your access point or your home router, it should show you a list of clients and the current data rate that they're connected at. Moving forward here. So how do I increase speed, right? So we're going to talk about just as general how the industry, not how you yourselves would increase speed, moving closer to the access point or whatever, but in the industry, how do we get faster and faster speeds? How do we go from 11 megabits 11B to 54 megabit speeds in 11G to, N600 and N and AC, 3800, 5800 and stuff. So how do we get those faster speeds that are advertised? So one way is doing by increasing your encoding. So we use something called QAM. So 64-bit QAM is what we used in 11N. With 11AC, we could jump all the way up, some devices up to 256 QAM. And now with Wi-Fi 6, we're up to 1024 QAM. So the question we get a lot is, well, wait a minute, if you can do this higher QAM, why didn't we do that back in the day? And the answer is, it takes a lot of computing horsepower to be able to take the data and encode it in such a way over the QAM, over the radio waves using these different bit rates of QAM. So basically, in the old days, we just didn't have the horsepower to be able to do it. Keep in mind also, not only do we have to have the horsepower in our access point, which is plugged into AC power, but you also need the same amount of power in your portable device for it to be able to decode and re-encode when it transmits back. So it takes a while to get to that point where we can do it efficiently enough power-wise to make it worthwhile. The other way we do it is by increasing the number of spatial streams that we're using, and I've got a slide on that in a minute here. And the other way to do that is by increasing bandwidth. 11G used 20 megahertz bandwidth, 11N could use up to 40 megahertz bandwidth at a time. 11AC Wave 1 did up to 80 megahertz, and the Wave 2 stuff does up to 160 megahertz bandwidth utilization. So we'll talk a little bit more in depth on a couple of these. So let's start here by talking about 2.4. So 2.4 gigahertz here in the United States gives us in the ballpark of around 60 megahertz of usable spectrum that's open for everybody to use. And when you go into your AP, you'll see, hey, I've got 11 channels to choose from. The trick is those channels are not spaced out properly. They are only about 5 megahertz wide channels, and again, you're using a 20 megahertz wide actual broadcast channel. So what that means is these channels are overlapping. So if you're broadcasting on channel 1 and somebody else is broadcasting on channel 2, you've got a huge amount of overlap that's going to cause interference. So when it comes to 2.4, using 20 megahertz channels, we've only got 3 channels in the US that we can use without causing any sort of overlap and interference between devices. And this is all being shared by your access points, your neighbor's access points, Bluetooth devices, wireless game controllers, basically anything that's Wi-Fi or anything that's wireless is either using 2.4 or 5, and most stuff, especially cheaper stuff, is using the 2.4 spectrum. So what that means is really quickly you run out of space. Now with 11N, we jumped up to 40 megahertz channels. So what that means is now you can only have one device broadcasting, right? Before another Wi-Fi device using a 20 megahertz channel is going to have some overlap and cause interruption. So those 40 megahertz channels in 2.4 didn't do us a lot of good. Oops, I guess I was getting ahead of myself here. It's showing how it works. So that's why there was a big push to 5 gigahertz, right? You might remember that there was a big push to dual band radios and moving stuff to 5 gigahertz. Well, why? Because we've got a lot more spectrum to use. If you go with 20 megahertz channels, you've got something like 25 non-overlapping channels, right? So good, right? We've solved this issue of overlap. We moved everyone to 5 gigahertz. We've now got 25 non-overlapping channels. It's great. We don't have to worry about our neighbors. We don't have to worry about interference, right? Yeah, not so much. First thing I want you to notice here is this middle section is orange and yellow. These are called DFS channels. These are channels that are used also by radar systems, including weather radar, airport radar, and are used by the military. So if you want to use these channels, what the FCC did is said, hey, great, you can use these channels provided nobody else is. So any wireless device that wants to use these channels has to constantly monitor those channels to make sure there is no military or radar using that frequency. And if it does detect that somebody else is using it, it has to immediately stop broadcasting on that channel and then either find another channel that's not being used or wait until that channel is no longer being used. And I think there's a so many minute countdown that it has to do. But the short version is, if your access point detects one of those, an event where radar or military is using that frequency, all your users are going to get kicked off. It's going to have to then scan for a new channel to use and then switch all of them over to that. So everyone's going to get disconnected for a few seconds. It can take up to a minute on these DFS channels because you have to monitor them before you can start broadcasting on them. So there's generally at least a 1 minute lag between when you detect radar and when you can start using those channels again. So a lot of people don't like that for obvious reasons. Another problem you run into is a lot of consumer equipment doesn't support these DFS channels. To get DFS certified, it can take up to 6 months on top of the normal FCC certification program. So for that reason, a lot of consumer devices don't use this. So you might not want to be using those in your home, but also in business, where people these days are all bringing their own phones and devices. We run into this constantly, where someone brings a laptop or a tablet or their phone, and it can't connect to your work access point. And after a bit of troubleshooting, we eventually figure out, okay, you're using a DFS channel, and your phone, for whatever reason, doesn't support DFS channels, so you can't connect to the access point. So because of that, what happens is a lot of people choose to just ignore those DFS channels entirely. It's too much hassle. So now you're going from 25 channels, right, to 9 non-overlapping channels. which gets us to our next thing. Everyone wants faster speed. So how do we do that? By increasing the bandwidth that we're using. So everyone now wants to go, okay, well, I want to use 40 megahertz channels to get faster speeds. So when you go up to 40 megahertz, you've only got 4 non-overlapping, non-DFS channels that you can use before you start getting into co-channel interference issues. And of course, like I said, with AC, we went up to 80 megahertz channels. So if you want the maximum speed that that product is being advertised for, you need a clean 80 megahertz channel. So there's only 2 of those available in the 5 gigahertz spectrum if you don't want to use DFS channels. And then, of course, the Wave 2 stuff jumped all the way up to 160 megahertz. So if you want to get that maximum speed that that Wave 2 AP is advertising, you have to use DFS channels. There's no way around it. But again, you're down to only 2. So as soon as you've got more than 2 access points within the same general area, you're going to start having interference issues. So that was increasing bandwidth and how that affects things. Now we'll talk a little bit about spatial streams. So if you remember, we talked about before, these Wi-Fi waves can bounce off of things, they can scatter, they can reflect. So that was something that back in the B and G days we called multipath problem. Basically, the receiver would hear the same sort of thing as sort of an echo, right? They'd hear the one stream, then they'd hear it bouncing off the ceiling, then they'd hear another stream, slightly delayed that bounced off of the wall. Since each of these paths are slightly different lengths of distance the signal traveled, they're arriving all spaced out slightly differently, creating sort of an echo effect. So it was a big challenge we had back in those early days, which is, geez, this, how do we determine which is the signal we want to hear, and how do we prevent these echoes from making it hard to understand the signal we want to hear? So somewhere along the line, somebody smarter than me figured out, hey, you know what? We can take advantage of this multipath. We've figured out a way to be able to recognize the signal we want versus an echo. And what we can do is we can use these different, these different paths the data can take, and we can send different data over each one. So it allows us to transmit different data simultaneously on different antennas. So these are what we call spatial streams now. So for each antenna you've got a different spatial stream where you can send different data simultaneously. So the most often way of doing this here, as we show in this example here, is you can send 2 150 megabit data streams. They follow different paths because the antennas are spaced differently, and there's some other stuff we can do to make sure they follow different paths. And the end device can receive 300 megabits of data at a time instead of only 150 megabits. The other thing we can do is something that was added in Wave 2 11AC products, which is called MU-MIMO. So instead of sending different data streams to one device, we can split those data streams and send those data streams to multiple devices. So you're still getting 350 megabits total data sent, but you're sending 150 megabits to one client device and 150 megabits to a different client device. So that works really well if you've got a lot of phones or tablets that have weak radios that only support one spatial stream, but your access point supports 3 spatial streams or 4 spatial streams. So you can divvy up those spatial streams instead of letting them go unused for those clients. So when you look at a lot of business class APs, instead of saying AC 2600 or AC 1200, you'll instead see them notated as 2x2, 3x3. So that's telling you the spatial streams. It's another way of conveying that data and making it a little bit more usable for you. So the first number is telling you how many spatial streams the device can transmit. The second number tells you how many spatial streams the device can receive. So most of the time those are matched, 2x2, 3x3, but occasionally, especially on client devices, you'll see 1x2. So it can only transmit 1 spatial stream, but it can receive 2 spatial streams. So you can send it 300 megabits of data, but it can only send back 150 megabits of data. And if you look particularly at Cisco equipment, you'll see something where they'll say like 4x4, and then they'll have a colon, and then they'll have a 3. So right, you'd say, well, it's a 4x4. I can send and receive 4 spatial streams. No. You can only send 3. That number after the colon is actually the maximum number of spatial streams it can actually handle at a time You've just got 4 antennas to choose from to get those 3 spatial streams. So from a real world perspective, it doesn't really make a lot of difference. It maybe gets you a little bit better speed or range, but it's marginal in the real world situations, which is why most people don't do that anymore. So to put that all together, we've got a little chart there showing you the number of spatial streams, the modulation type, and how wide the channel is to show you the different speeds. So just to keep it easy and simple here, at a 1x1 11 AC device will advertise a 900 megabit speed. It's actually 866, which is over here. So that's being measured by looking at a 160 megahertz channel, 256 QAM. But there's a good chance, especially if you're using this in a home or office or an apartment or an office where there's a lot of other devices around, you won't be able to use a 160 megahertz channel. You might only be able to use an 80 megahertz channel before interference makes it unusable. So that'll drop your speed to 433. If because of noise ratio you can't make 256 QAM work, you got to drop back to 64 QAM. Well, now your speeds drop back to 325. So anyway, you can see how that plays out across the board there. So that's where the speeds are and what determines the maximum data rate you're going to be able to make. So this is another question we get a lot. How many devices do I get to put on this access point? This access point says it supports 64 clients. This access point says it supports 1,000. I want the 1,000 one, right? Well, no. So in the real world, whatever spec you see on the data sheet for how many client devices can be supported is a theoretical maximum. Because of the way Wi-Fi works, you're going to run into limitations and bad experience long before you get anywhere close to the number of associations that you see on that data sheet. So what determines how many devices you can get on there has to do with the density, the type of device, how many spatial streams they support, what the application requires. VoIP, for instance, even though it uses almost no bandwidth, is really, really demanding as far as that the airtime be free for that device to be able to transmit, versus Netflix, where downloading 4K uses a lot of bandwidth, but it's not really picky because it can buffer the data, so it's not really picky about packets being dropped here and there or packets coming in out of order. Whereas when you're having that VoIP conversation, it's really important that no packets get dropped and that all the packets come in order, because otherwise you can't buffer, because otherwise there's too much of a delay and you can't have that two-way conversation. So it doesn't matter really whose access point or which model of access point you're looking for, unless the number of client devices supported is ridiculously small, you're generally going to run into problems well before you get anywhere near to the theoretical maximum number of devices, just due to the way Wi-Fi works. So we've got a real-world example for you, which will hopefully make this here. Oops, and Joe had a question for me a couple slides ago. Let me finish this slide, and then I'll go back and answer your question, Joe. So we've got a simulated scenario here for you. Basically, we're simulating, so no matter what the type of client device, it's got the same signal strength, it's operating on 5 gigahertz, and it's using a simple 20 megahertz channel, the one least prone to interference out there. And what we've done is we've simulated using a 3 megabit stream. So that's what? That's like a 720p YouTube stream, I think. So if you have a laptop that supports 3 spatial streams, we can get 34 laptops on there, all being able to transmit and handle that 3 megabit stream. Gives us an aggregated data of 100 megabits, aggregated data over the wireless network. If we drop them to a tablet, and the only thing we're changing is the number of spatial streams supported. So we go to a device that only supports 2 spatial streams. Well, now we can only fit 21 devices on that wireless network before we start having issues. So it gives us 65 megabits total. So why is that? Because again, using multiple spatial streams, it either lets us transmit more data at once, whether it's to one device or we're using MU-MIMO and spreading it out. So when you've got an AP that supports 3 spatial streams, but your client devices only support 2, you're basically dropping a third of your bandwidth that's available for all your devices to use. And now we go down here to a cheap Android smartphone that only supports one spatial stream. We can only get 10 devices on that same wireless access point streaming that same 3 megabit stream. So you can see what a difference it makes to the number of devices that we're looking at and the aggregated throughput for those devices just by changing how many spatial streams are supported by those devices. And then you start throwing in other real-world things in there, which is signal strength and stuff like that. And these devices don't support the faster speeds and whatnot. You can see how the real world affects things like that. And again, if you're doing VoIP, you might not even be able to get that, not because we've hit a maximum amount of bandwidth, but because of the type of data that's being sent and that it needs to be sent sequentially. So VoIP is actually surprisingly demanding, although you wouldn't see it in this example because this is just looking at the overall bandwidth. Okay, so you've heard me talking a lot about signal-to-noise ratio, interference, things like that. So we'll talk a little bit more about it. Oh, wait, I forgot. I want to go back here to Joe. So let's answer Joe's question. So Joe was asking, does DFS limitation make Wave 2 APs not useful in areas near airports? So the answer is maybe. It depends, just on where you are. I'm nowhere near an airport, and yet I will have DFS hits. I'm guessing probably from the local TV weather radar, which occasionally goes out. You can stay away from the weather radar and try to stay on the other ends of that DFS spectrum, and you'll be less prone to get hits, but you still may get hits. You may still get stuff going on out there, false hits maybe, and actually the military using that frequency. But because of the way it is, we have to be very careful that if we see anything that might be the military or the other government agency using that channel, we have to turn it off and find a new channel. So it's always one of those things that's iffy, and it just depends where you are as to how likely you are to run into problems with it. The other question, Joe, just sent a follow-up asking, how do you tell if you're in an area that uses a lot? And as far as I know, there's no way to know other than sticking up an access point, using DFS channels, and seeing how often you get disconnected. In general, it's not going to happen often, but it is going to happen occasionally, no matter where you are. So obviously, if you're near an airport or something like that, it may happen more often. You can play around and try to choose different channels. We had a customer who I won't name. They were a WISP, and they were using DFS channels only for their backhaul. And they ended up just throwing in the towel because even though they cover a large area and most of it theoretically shouldn't have any sort of DFS hits, they were still getting disconnected often enough that it was just a pain for them to be able to maintain, and they'd get customer complaints. Albert is asking, does satellite like Dish have any interference? So no, the satellite dish itself shouldn't. I don't know off the top of my head what frequency they are using. But it isn't one of the 2.4 or 5 gigahertz that we use. They've got their own licensed chunk of spectrum that each one of the satellite providers uses, so that shouldn't cause any interference. And Pat sent in a comment here just saying that, if you're close to the coast, you're very often going to run into hits from the Navy using stuff out there. Or me, I'm inland. I'm at 600 feet above sea level. And I've got a naval base just on the other side of town from where I am, operating out of a lake. So even being inland a bit doesn't necessarily help you out there as far as avoiding the Navy. Okay, anyways, going on now, let's start talking a little bit about code channel interference and the best way to solve it. So as I mentioned earlier, when it comes to radio waves, right, only one device can transmit data at a time. If 2 or more devices transmit data, the signals combine in weird ways and becomes unintelligible. A good analogy to this would be, if you played with those old analog walkie-talkies as a kid, if you had more than 2 of them, you had a group of friends that were using them, you probably ran into situations where there was interference. Even on digital radios, if you were using one that somebody else is using the same channel as you out camping somewhere, you might run into garbles when both you and them try to transmit at the same time. Or alternately, if you've ever been driving, listening to AM radio out in the middle of nowhere, and you get to that situation where you've got 2 nearby channels and they sort of overlap each other, it's the same sort of thing that happens with Wi-Fi. Because we're using unlicensed 2.4 or 5 gigahertz spectrum, there are lots and lots of devices that are using that spectrum. There's only those 3 bands that I talked about before that people can use. So you're going to get interference. You also just get interference from industrial devices. In my home, when my air conditioner kicks on, I notice a performance drop just because the blower or something in there is putting out RF that probably it shouldn't. And when you're talking about commercial buildings, anything that's designed to be sold into the home has to comply with FCC Class B regulations, which regulate, in theory, how much RF interference they can put out. But when you're in a commercial environment, anything that's designed to be sold to businesses does not have to comply. So a lot of that stuff puts out noise that you wouldn't actually expect it to be doing. So anyway, that causes co-channel interference. Probably the most common problem that you're going to run into is having multiple APs within range of each other using the same channel. So traditionally, the way we dealt with this is, you very carefully plot out where each of your access points is going to go, and you try to choose a channel. Okay, this one's on channel 1, this one's on channel 6, this one's on channel 11, and try to minimize how much overlap they have in their coverage areas. So you would try to then reduce the power of those access points to reduce the interference, which it absolutely does work. You reduce your power, you reduce the interference between those APs and the amount of overlap, which is great. The problem is you're also lowering your signal strength, so you normally end up also with signal-to-noise ratio problems because you've now lowered the strength of your signal versus the level of the noise in the environment that aren't caused by other access points. So oftentimes by lowering the channel, you end up getting yourself into a situation where the overall available bandwidth ends up being the same, or the maximum speed you can achieve is the same as if you just left the power at full and just dealt with drop packets and retransmits. So the best solution for this is smart antenna. So traditional APs, right, you mount them on the ceiling, they sort of form sort of a circular umbrella type coverage pattern. If you have a directional antenna or a panel antenna, those will focus the beam on a very narrow area. So that's how you traditionally do it. So smart antenna basically has a bunch of different antenna pattern configurations that aren't circles and aren't necessarily narrow points, and it's able to basically look at the environment and figure out, based both on where that client is in relationship to the access point, but also with the algorithm we're using, we spend a lot of time looking at other sources of RF noise and can choose an antenna pattern that maximizes signal getting to the client, but also minimizes the amount of co-channel interference that our antennas will pick up and have to weed through. So this is something, unlike some of the other technologies out there, that requires nothing special on the client device. So it'll work with any vendor, any brand of client device. And it works even if the client device moves. It can, in basically real time, change the antenna patterns as the client moves or as sources of other RF interference moves. So it's really good for you in, if you're putting up APs in an office building where you're not controlling the network on the floor above or your neighbor next door. It's good in apartment buildings. It's really good in concert venues, conference rooms, things like that, where you've got a lot of open air and you've got a ton of client devices in the same area. So we put together this test scenario. This is using our NWA 1302. This is that inexpensive wall mount AP that's designed for hospitality that has smart antenna. And we're comparing it with Ubiquiti, which is the same form factor, basically the same RF specs, just minus the smart antenna. So in this scenario here, this is a hotel where each hotel room has one of these low-powered access points in them. You see we've gone through there and picked out channels to make sure we're not overlapping with our next door neighbor. So we've always got at least one room between the APs before there's any sort of interference. So what we did is we went through here and we connected 2 client devices to each access point. So when we turned on just one AP on the channel that we were using, you will see here that us and Ubiquiti are about the same. And technically, Ubiquiti beat us by 2 megabits per second. So with one AP operating on that channel, there's no interference. Both of them are able to use about 67% of the available airtime with 2 wireless client devices connected to them. When we turn on a second AP, again spaced out so they're not directly next to each other, using that same channel, what you see here is the aggregated throughput for both of those APs. For us is 785 megabits per second. And for Ubiquiti, it's only 555 megabits per second. If you look at the AP breakdown here, you'll see both of our APs are getting about 400 megabits per second. Where with Ubiquiti, one's getting 400, the other's getting about 200. Right, so we know at 400, they're using about 67% of the available airtime. And then you throw in the second AP, it fills in that gap, so now you're using 95% of the available airtime. But if you look over here with Smart Antenna, you'll see we're able to use 131%. So 31% more airtime than is theoretically available. Why? Because by using Smart Antenna, the devices can transmit at the same time on different APs and not cause interference, because the Smart Antenna is able to essentially ignore that noise or that interference coming from the client devices for the other AP. So again, same thing here, we'll turn on a third AP using the same channel. And you'll notice here, I guess I accidentally deleted the speeds, but you'll see here we've got over 900 megabits aggregated speed. We're up to 155% of the theoretical maximum airtime utilization. And the Ubiquiti's actually dropped to 91% airtime from 95 with just two APs. And that just has to come with how, Wi-Fi, like I said, it uses a sort of random number generator to determine whether to check, when to check to see if someone else is transmitting. So you end up in a situation where you're not using the available airtime as efficiently. And you'll also notice again that when you look at ours, the throughput is pretty much consistent no matter which AP we're talking about. Where with Ubiquiti, the speeds and overall throughput for each AP is highly variable. And if we did a sort of a time chart on here, you would see it switches back and forth between which APs are getting most of the airtime. So that's it. That just shows you how Smart Antenna works in this one scenario. But anytime you're dealing with a lot of interference, whether it's interference from other APs or whether it's interference from lots of client devices trying to talk to the same access point, Smart Antenna makes a world of difference. So now we'll start talking about some other stuff here. And Jack was asking if we have a matrix with the list all the Wi-Fi's with Smart Antenna, and the answer to that is yes, we do. Reach out to Jacob or Ivan or Sandy, whoever your salesperson is, and they can get that for you. Sorry, trying to get my slides to advance. There we go. So now I want to talk about something else that goes on a lot. This is a common mistake we see. So as I mentioned before, your traditional round access point or square access point is designed to be mounted on the ceiling. It sends out the signal in roughly a circular pattern, sort of an umbrella shape going out from the access point, trying to cover as much area underneath it as it can. And oftentimes, for whatever reason, you can't mount an access point on the ceiling. You don't have permission, the ceiling isn't there, so what we see is people mounting ceiling-based access points on the wall. So, I mean, it does work, but you end up sending a lot of your signal up into the ceiling where no one's at or down into the floor, or causing interference on those floors above and below you, and just generally getting sort of a poor coverage area in the area you're trying to cover. So Smart Antenna is something that can help solve this. The Smart Antenna can go through its antenna patterns and find one that works for wall mount. We also have a number of access points that have something that we call dual optimized antennas. And I really wish we would have come up with a more catchy, shorter name for it than that. But basically, we've built into these access points two different sets of antennas. One set of antenna that's designed for the ceiling, one set of antennas that are designed for being mounted on the wall. And then you can switch back and forth as to which pattern you want based on where you've installed that access point. So that's another way of solving this sort of issue and making it perform a little bit better. So just some general mounting tips. Where do I mount my access point? In general, you want to mount it as high up as possible, so on the ceiling, and you want to try to mount it in a centralized area to cover the maximum amount of space. So generally higher is better within reason. You run into, if you've got huge vaulted ceilings or something like that, I'm thinking like in a concourse area at a convention center, that might not be the best idea. just because of how far out that signal will go and just how much distance there is between the client device and the AP. But in general, you want to mount them on the ceiling. Generally will give you the shortest distance between the client devices and the AP without having to go through obstructions. So it's better to go a little extra distance over the air than it is to penetrate through a cubicle wall or a person or an elevator shaft or something like that. So that's generally where you're wanting to mount it. You know, drop ceilings don't have that much attenuation. They aren't going to harm the signal that much. So we also, you know, often run into people saying, you know, oh, the client doesn't want us to poke holes in their drop ceiling, or I don't want to buy drop ceiling mounts, whatever. You don't need to necessarily. If they've got a drop ceiling, just rest the AP on top of the drop ceiling, you know, pointing down as if you had mounted to it, but just lay it on top there. And generally that works pretty well for people. You don't have to put any screws or holes in anything. The cords are out of the way. And that drop ceiling, unless you're putting it directly on the T-bar, isn't going to cause much negative impact on that access point. So that's a little tip or trick there for you. You know, if you are mounting it on the physical ceiling, well above the drop ceiling, keep in mind that, you know, metal HVAC ducts, you know, metal conduit, things like that are going to cause interference. So you don't want to mount them onto a physical ceiling if they're going to be surrounded by that. You will want to drop them down a bit from there. We've got some questions. Let's answer some questions. Martin, what is Martin asking? If the ceiling mounted device is placed flat above the ceiling tile and placed flat, what direction the signal, upwards or downwards? So you would want to mount it facing the same way you would as if you were mounting it to the ceiling. So in the case of our APs, that would mean the Zycel logo is facing down towards the ground, and the belly label with the model number and FCC information is facing up towards the sky. So that's the way you want to do it. So it's still the same position. So yeah, pointing down. Just some strategies here for hotels. You know, the traditional way of doing this has been you put APs out in the hallway, and then you try to cover anywhere from 4 to 8 to 16 rooms from one access point. What we're seeing is this is going away. It started on the more expensive hotels, but we're starting to see this now more and more, even on lower tier hotels, is a move to putting APs in the rooms themselves, either one per room or one per every other room. That's what we use that NWA 1302 or the WAC 5302 for. So this is the new strategy, and the answer for that is, you know, why are they doing that is just because, you know, hotel owners don't like complaints. They don't like people complaining about the wireless network. So if you've got one just sitting out in the hall, you know, it may be that their cheap Android phone or their cheap Amazon tablet doesn't have the signal strength to go through the 2 walls and the bath shower to be able to get their signal back to that access point. So that's an issue you run into. You run into an issue now just with families traveling. They have a lot of Wi-Fi devices. In the old day, you had your laptop. Then it was you had your laptop and your phone. Now you've got your laptop, your phone, your handheld game console, you know, your Switch, etc. So we're getting more and more people on those access points, and they're just overwhelming the wall mount access point. And then just what people are doing. It used to be people would just browse the web, right? You download 100K of information and sit there for 30 seconds before you load the next 100K. Where now people in their hotel are wanting to stream Netflix, YouTube, et cetera, et cetera. So that's why we're seeing more and more people moving to this one AP per room or per every other room. So things to look for if you're mounting them in the rooms is you want APs where you can turn off the LEDs, because nobody wants a blue or orange flashing light directly above their head when they're trying to sleep. You also want to take a look at mounts and make sure you get APs that have mounts that support locking. So a number of APs are designed to make it harder to remove them, because guests, believe it or not, will steal APs out of rooms and anything else that's not locked down. Public areas in the hotel, you know, when you determine how many APs you need to think about the density, how many users are really going to be connecting there. You know, the more users that are going to be in the area, the more APs you need. That's generally more important than the physical size of the area, generally. You know, use load balancing and client steering. And it's a good idea to break up your coverage based on area. So put the lobby on its own network, separate from the pool, separate from the cafe, Give them their own coverage areas and their own VLANs is generally the best way to do that. And again, if you're dealing in areas where there's a lot of users, go to Smart Antenna. For schools, it's the same sort of thing here. You want to ask yourself how many students are in the room and how many of those students are going to be connected to a Wi-Fi device. Some classrooms it's just a few people. Some classrooms are smart classrooms where every single student is connected to a Chromecast or a tablet. They connect to the Wi-Fi. And then is the teacher using smart streaming apps? Or are they using a smart billboard or a whiteboard? Are they streaming video to each student's device? Some classrooms that's a yes. Some classrooms, no, they just connect to the Wi-Fi to do some research or send email or submit an assignment. So you have to take that in mind. If they're streaming a lot of video to each of those clients at the same time, you may need 2 APs per room. Always a good idea, no matter how many APs or students you're using, because generally you've got a high density of users in a small area. Always a good idea to use a smart antenna. Both Nebula and our wireless LAN controllers have a special smart classroom mode that tweaks the way we do load balancing to optimize it for a school situation where you've literally got 25, 30 students all connecting simultaneously to the same access points. In general, teachers need to be on their own network. You don't need their own hardware. You just use VLANs and give them their own SSID. So students are not on the same network as the teachers generally. Once you get to about 20 students on there, you need 2 APs per classroom. And you absolutely need smart antenna if you've got 30 or more students in the same classroom. So now we'll talk briefly about Wi-Fi 6, aka 802.11ax. So let's talk a little bit about it. So 802.11ax is the new strategy or the new type of doing Wi-Fi, and it makes a ton of improvements to how Wi-Fi works. It makes tremendous steps towards solving co-channel interference issues. It makes tremendous steps to solving the problem with inefficient use of airtime, inability to know if other clients are transmitting. So Wi-Fi 6, in theory, solves a lot of those issues for us. So first thing here, 802.11ac only worked on the 5 gigahertz radio. Wi-Fi 6 is designed to work on any frequency, 2.4 or 5. Anything new they open up in the future should, in theory, all work just fine with Wi-Fi 6. In high-density environments, so that means lots of users in the same area, it more than doubles the amount of actual throughput you can achieve when everyone's still connected at the same data rate. So, the difference we talked before about data rate and throughput, same sort of thing here. It should make a huge difference for us in those things. So it gives us some new stuff. 1024-bit QAM, which we talked about earlier. OFDMA, this is a huge game changer, which controls the ability of the AP to manage and assign slots of time to each individual client device, so you don't have to worry about clients interfering with each other. MU-MIMO now works not only from the AP to the client, but can also work from multiple clients transmitting back to the AP, something that's not supported in AC Wave 2. The ability to do spatial frequency reuse, the ability to do what they call BSS color coding, all sorts of really cool stuff that should make a huge difference and simplify everybody's life in the future. The downside is most of these things require that all the client devices also support Wi-Fi 6. So it's going to still be a few more years before you really start seeing the benefits of Wi-Fi 6, even if you put in Wi-Fi 6 APs today. So when it comes to Wi-Fi 6, Wi-Fi 6 certification from the Wi-Fi Alliance just started back at the end of October, I believe it was. But the IEEE, the group that makes the overall standard, these still haven't actually finalized the standard. The last time I checked, it was expected to be finalized in September of 2020. So, obviously the chipset vendors, the hardware manufacturers, even the Wi-Fi Alliance are sort of running ahead of the actual standard and trying to get things out there now that they're calling Wi-Fi 6 to sell new hardware that maybe not necessarily are. So basically there's been different generations of Wi-Fi 6 chipset, and most of the key important features for Wi-Fi 6 weren't supported on those early devices. So we've got an example here. This is using Qualcomm. The two big chipset vendors are Qualcomm and Broadcom. I only have Qualcomm on this slide. Broadcom is a very similar situation. So basically, the Qualcomm Gen 2 chipsets didn't start shipping to manufacturers for doing stuff with them until the end of August this year. So anything that launched before August of this year, whether Broadcom or Qualcomm, Broadcom's timeline was basically the same. I think maybe they were two or 3 weeks ahead of Qualcomm. But basically anything that came out before August of this year, and realistically probably before October of this year, is probably using a Gen 1 chipset. So Gen 1 chipsets and Qualcomm will never support upstream OFDMA. They'll only support downstream. They won't support upstream MIMO. They won't support what's called TWT. They won't support BSS color coding. No plans to upgrade them to that. The hardware itself is just physically incapable of supporting those features. And some of those features like TWT and BSS color coding are the things that you want to make deploying Wi-Fi easier and to solve a lot of these issues that we have with interference and things like that. So it's something to keep in mind when you're looking at Wi-Fi 6, and most manufacturers aren't going to tell you what generation of chipset they're using, whether it's 1.0, 1.1, 1.2. So like I said, a good rule of thumb is if it launched in the market before August of this year, it's probably a Gen 1 chip and is never going to get the Gen 2 upgrades. There are still vendors that just recently launched product using Gen 1 chips because the Gen 1 chips are still there and they're cheap. And you get to call it Wi-Fi 6 in your advertising even though the features aren't supported. So it may be helpful to know some of the features that give you help that are beneficial for your environment, BSS color coding, upstream OFDMA, et cetera, and just look for those features. Are those features on the data sheet? And if they're not, then chances are it's the older chip and won't be upgraded to it. Another trick that's going in here is with the Qualcomm Gen 2 stuff, and that's what we're using in all of our Wi-Fi 6 APs, at least on the business side of things. I don't know what they're doing on the service provider, but we're using the Gen 2 Qualcomm, which is great. The hardware, in theory, is going to support all of the features that are in the official IEEE standard when it gets certified, but they aren't supported today. So some of these, there's going to have to be firmware updates pushed out to add these features in the future. Right now, the belief that, and what we're being told is that the code from the chipset vendor should be ready by the end of Q2 that supports all of the key features. And then by the time the Wi-Fi Alliance, IEEE standard finally gets ratified, there will probably be another firmware update to tweak how things are implemented to match the final spec versus matching the draft spec. So just keep that in mind also. Going forward, you will need to do firmware updates to get all of these features that aren't all there today. And then again, the client devices need to have chipsets that support these features and software that supports these features as well. So again, before we can take full advantage of Wi-Fi 6, we're probably 18 to 2 years out before you really start seeing the benefits. So with that, that concludes today's presentation. I hope that was okay. Sorry about starting a minute or two late there for you guys. So go ahead, and if you have any other questions, you can send them in using the Q&A box. Just also in general, just to make you aware, we do have support forums where you can talk to other users. These support forums are also directly monitored by our R&D team, and the R&D team will weigh in and answer questions there. Just go to forum.zycel.com. We've got two forums, one for business products, one for consumer products. Check them out if you haven't already. If you've got something that doesn't require an immediate solution, or you've got some feedback, post it there. People at our HQ in R&D and product management will see those comments, will see those posts, and may respond to you. And just in general, if you have feedback on today's presentation, you have ideas on new topics or different things you'd like to see us talk about in the future, either me or Troy, feel free to email me directly or reach out to your salesperson and we can help you out with that. Okay, so Harold is asking a question. We've got some questions coming in here. So Harold asks, please talk about Wi-Fi 6 and mesh. So Wi-Fi 6 and mesh are two different things that aren't related to each other. There may be Wi-Fi 6 products that support mesh. There's plenty of non-Wi-Fi 6 products that support mesh. Mesh is not part of the core Wi-Fi 6 standard. It's its own thing. So for us, we have our own smart mesh technology we use on our business products to allow them to talk to each other. And that's something that's supported by Nebula. We've got another slightly different version of mesh that's supported by our wireless LAN controllers. So if you're using a USG or UAG to control your network, it has a slightly different implementation of mesh. Out in the industry for consumers, everybody's got their own Orbi, VLOP, stuff like that, Multi, consumer mesh. Those are generally proprietary. There is something new out there. I want to say it's called Easy Mesh that the Wi-Fi Alliance is certifying. So Easy Mesh is the idea is that you'd be able to have vendor agnostic mesh. So you'd be able to take a Zycel consumer mesh AP and take an Orbi mesh AP, and they would be able to talk to each other and form a mesh together. So the Wi-Fi Alliance does have that certification. I don't know how it is for Broadcom, but I know Qualcomm, the support for it isn't great. It does not work well at the moment. So at some point we will roll it out to our consumer products if and when the code we get from Qualcomm that supports it is high enough quality to make it worthwhile to release it without it causing issues. So those are the different types of mesh that are out there. The Easy Mesh is primarily aimed at, my mouse is doing funny things. There we go. So the Easy Mesh that the Wi-Fi Alliance push out, as far as I know, is primarily aimed just at the consumer mesh. I don't know if anybody is ever going to adopt it for business mesh type stuff. Next question, this one's from Jack. In a very high usage area, do you suggest using smart steering to reduce station signals threshold? That is something that comes up to be beneficial. That's another thing that I didn't talk about in today's presentation, but when it comes to roaming between access points, roaming is actually handled by the client device, not the access point. So behavior when it comes to roaming can vary greatly based on the device and how that vendor has implemented their roaming algorithm. iPhones, for instance, are very famous for connecting to a single AP and then never wanting to roam, no matter how weak that AP gets and how strong other APs using the same SSID are close to them. So the Wi-Fi IEEE group, there's some other standards out there called 802.11k and V that are designed to give the AP the ability to sort of steer those clients to different devices. But again, it requires the client device also support that standard, and oftentimes they don't. So the other thing you can do is talk about what Jack is asking about is we have a smart steering function, so we can set that up to automatically disconnect a client device when their signal strength drops below a certain threshold. So basically the AP can say, hey, wait a minute, your signal is getting weak. I bet you they're probably closer to another AP, and we'll disconnect them at least temporarily to try to force them to roam to another nearby AP. So yeah, it's absolutely something you can do in a dense environment to try to force all client devices to roam much more frequently and not slow down that particular access point. And again, if I'm answering your questions and I didn't answer your question properly or you have a follow-up, feel free to send it in. I will get to it. Next is from Brett. Even though Wi-Fi 6 features are not in client devices yet, will the Wi-Fi 6 AP still be compatible with legacy Wi-Fi? So yes, they are still compatible with legacy Wi-Fi. They will still connect with A, B, G, A, C, and clients. So yeah, you absolutely can deploy Wi-Fi 6 today. Just keep in mind that a lot of those key benefits that Wi-Fi 6 gives you, you won't really see those in the future. But yeah, absolutely, deploy Wi-Fi 6 today. Yeah, you're helping to future-proof your network. But again, I would at least keep an eye and try to buy something that's using the Gen 2 Broadcom or Gen 2 Qualcomm chipsets, so you get all those features when they finally become available. Jack also is asking, other than smart antenna, what should you be considering for high usage areas? I mean, smart antenna is the best thing you can do. Honestly, it is. Some of the other things you can do, You can look at doing things like we talked about before, kicking off slower clients, trying to force them to roam. You want to try to do channel steering, try to get as many people on 5 gigahertz as possible. Other things you can do is put in a lot of access points and drop the power down, use directional antennas to try to cover a smaller area to reduce interference between APs. It also depends on what type of traffic they're doing. If they're not doing VoIP, if they're just doing, basic guest access or something like that, you might think about, if you've got a lot of APs, lowering the channel bandwidth to 20 megahertz or 40 megahertz channels to reduce interference between APs. So those are all sort of things you can do there to help out those. Whoops. So Harold's asking, will your existing mesh APs work with Wi-Fi 6? What is the answer to that question? I just had that answer come in. I believe the answer to that is our Wi-Fi 6 APs will support our smart mesh. So they should be able to then mesh with our non-Wi-Fi 6 APs. But I can't remember if the support is there right now or if the support will be added later. I would have to look into that. So I'm pretty confident Smart Mesh is coming to all the Wi-Fi 6 APs, but I don't think it's necessarily there at launch. But it should eventually get there. Another question here. Gustavo is asking if this is being recorded. It is recorded. Double checking here that I did manage to record it. And yeah, it is still recording to the cloud. So yeah, you should be able to watch this. I've also done this presentation before, so there should be previous versions of this that are out there. You can reach out to your salesperson if you're having a hard time finding the link. Yeah, so Harold just says some more stuff on the Wi-Fi 6. So yeah, ASUS and some of the other vendors out there on the consumer side are offering consumer mesh. Like I said, we will have smart mesh coming to our Wi-Fi 6 business APs at some point in the future. But yeah, absolutely, there are mesh Wi-Fi 6 devices in the market on the consumer side of things right now. There may be some on the business side. Can't remember any off the top of my head, but I think maybe Ruckus does. I don't know off the top of my head. So Jack is asking here, are there any particular tool you use on site to determine signal strength, quality, signal overlap, etc.? There's a number of different tools out there that you can use. Some are cheap, or some are free, some are more expensive, some of them you have to pay for. So there's some really, powerful tools out there where you can, scan in somebody's floor plan, and you can assign walls and what the materials are and drop APs in, and it'll try to simulate the environment. So those are out there. Ekahau has a tool for free called Heatmapper that I personally like. It's been around forever. There may be better stuff out there now, but it's what I'm used to. So Ekahau Heatmapper, it's a free tool, and basically you load in your floor plan, you connect to an AP, and you sort of walk around to different locations, and you click and basically tell it, and it'll tell you what the signal strength is right where you are. So you walk around doing that, and it creates a nice heat map showing you where the signal strength is at different places for different APs. Marcus has another tool that he likes, and I do not remember the name of it off my head. For Android, there's a really simple, really easy free tool called Wi-Fi Analyzer. I use that a lot in a pinch, just to give me an idea of what's going on in the environment. And then there's dedicated spectrum analyzer tools you can buy out there, which go even more in depth and help pick up a lot of stuff that the Wi-Fi tools. Most of the Wi-Fi tools are based on the Wi-Fi client in your laptop or in your phone, and they only really look at Wi-Fi. So you need a real spectrum analyzer to see everything else that might be causing interference. So those are out there. Sorry, I can't be more specific than that, but it should give you a couple ideas of things to use. We also do have a free tool out there. What is it called? Wi-Fi Planner or Wi-Fi something that you can download for free off our website. It'll let you load a floor plan in there, It'll let you load in our different APs. It doesn't show you real world coverage. It doesn't simulate walls and stuff. So it's not really useful for that, but it is, it does work quite well though if you're trying to provide a simple, easy floor plan map to your customer to say, you know, we're going to give you 8 APs, here's where we want to put them. You can go in there and tweak the power. I would tweak the power to 25%, and it'll give you a rough idea of the coverage area for where you're doing stuff. So it's a quick and dirty way of giving yourself a floor plan with APs mapped onto it. Okay, I'm not seeing any more questions. If you're typing something in, highlight it real quick, hit copy, and then email it to me. Again, my email is seanr@zicel.com, and I'll respond to you via email. But otherwise, our webinar is done today. Thanks for joining us, guys. And as always, you know, send us feedback. We'd love to know what other topics you'd like to hear about or how we can make these presentations better for you.